And in today's tutorial, we are going to look at strand 4, which is computational thinking, sub-strand 2, algorithm. Content standard will be taken from basic 7, strand 4, sub-strand 2, content standard 1. And in today's lesson, our performance indicator or indicators are going to be basic 7, strand 4, sub-strand 2, content standard 1, indicator 1. And in our indicator 1, we are going to understand the use of sequence, selection, and loop in writing a program. Describe the meaning of terms, algorithm, decomposition, and abstraction. Our second indicator is also going to base on how to perform a linear search. Now, behind all the softwares we use on daily basis, there is a code being run with all sorts of terms and symbols. Surprisingly, it can often be broken down into 3 simple programming structures called sequences, selections, and loops. These come together to form the most basic instructions and algorithm for all types of softwares. So let's look at the first programming structure in algorithm. Sequence. A sequence is a series of actions that is completed in a specific order. That is to say that action 1 is performed, then action 2, then action 3, etc. until all the actions in the sequence has been carried out. Below is my diagram. As indicated in the explanation, sequence is a series of actions that is completed in a specific order. So action A or 1 has to be performed, then action B or 2, then action C or 3, then action D or 4, until all the actions in the sequence is completed. Now let's come to the classroom scenario. We start counting numbers from 1. So it means that we will start from 1, then we go to 2, then we go to 3, then we go to 4, and on and on we go. So sequence is just to tell us that an action is performed in a specific order. In sequence, there is no room for random actions, no, but rather in a sequential order, one after the other. No trespassing, no jumping. Let's take this example. Itinerary for a day in a logic sequence. I wake up in the morning, then I take a water, then I go and take my bath, then I take my breakfast. So this is my logical sequence for each morning. Now, someone's sequence will also be different. Let's say he or she wakes up in the morning and decided to what? To take a bath first, eat his or her breakfast, then take water. That is someone's sequence. Now, another one's sequence or someone's or another person's sequence may be that when he wakes up or when she wakes up, she takes her breakfast first, then she bath, then she take water. All these examples shows a sequence of different types of people. Okay, but at the bottom line, there is a logical sequence in everything. It means that one step has to come, then followed by the next step, then followed by the next step, then followed by the last step. So things being done in a logical manner or in a logical sense is what we call what? Sequence. You can't jump. What you usually do is what you do. Eh? From 1 to 2 to 3 and to 4. Okay? So that is a sequence. Selection. Selections are a bit different. Instead of following a specific order of events, they ask a question in order to figure out which path to take next. Okay, so in selections, there will be a question for a decision to be made. After the decision is being taken, then there is a way forward for the program. Okay, let's take this diagram here for instance. You start your journey from the top, then you reach here. There will be a question here whether to pick yes or no. So, dependent on your answer, then the game will move forward or the program will move forward. So, when you reach at the question side and they ask you, do you want to go to the next round or stick to the current round? If you pick go to the next round, then the game will forward. But if you say no, stay in the current round, then the game will still be there and you'll be playing the same type of game. Okay, so in the selection, there are questions and decisions to be made. So if you see the question and you decided what you take will send you to the next level. So that is selection. So in most of our programs, we have selections to do or to take. So depending on the selection or the decision you have taken, then you can move forward or you know what lies ahead of you in the next paragraph. Now, let's take this example here in my diagram. You decided to take your toothbrush and let me say brush your teeth. So getting into your washroom, you have seen that you are run out of a toothpaste whilst your brush is there and your cap is there. So there will be a question. Do I have any more toothpaste? If my answer is yes, then I go in for the toothpaste. But if my answer is no, then I have to make a provision to go and buy a new toothpaste. So in selection, you have a question, then you have a decision to choose from or option to choose from. Okay, so without the question, you may not have options. So with the question, you will have options to move forward or not. So in a programming, you have a lot of options in programs. Okay, so if you are writing a program, you come to a stage where you have to make an option. You have to take a decision. Sometimes yes or no, simple as that, or true or false. Okay, in some of our tests, we have true or false. Yes. So when you get there, if it is true, you pick it. If it's false, you go. All right. Loops or iteration. The third programming structure is a loop. Like selections, loops ask questions. However, the difference is that they ask the same question over and over and over again until a certain task is complete. This is often called iteration. In my diagram here, This represents how loops looks like in the description above. So, you will continue to ask a question in a cyclical form. You continue to ask that same question until you get the right task or the right answer to that question. In my second diagram, there is a gentleman hammer here and there is a nail. Now, when you start hammering this nail, you keep on asking yourself this question: is the nail all the way in? So as you keep hammering, you are asking yourself this question until the head of the nail is inside the wood itself. Then you said, yes, now it is in. But when you were hammering, the continual answers that you are getting is no, no, no. It means that the nail is not all the way in yet. So you will continue to be getting the no response until all the nail gets in, then you have your answer yes. So that is how loops works. Okay, you will continue to ask yourself the same question over and over again until you are satisfied that this last answer will solve my problem for me. Now let's take a look at the summary of what we've just learned. The three structures of any programming structure. The first one we looked at what? Sequence. And we say sequence is a series of uh, steps, or it's a series of actions that is performed at a specified order of time. Okay. Yeah. All right. So in a sequence, we say sequence is a series of actions that is being performed at a specified order or specific order. So it means that the first action have to be performed before you move on to the next action. And so all the actions in the sequence are catered for. Now we look at the second structure as selection. And in selection, we said that there is a question. So until that question comes and the decision or the selection you will make will tell the system whether to go forward or not. So in selections, there is always a take-in questions. Then based on the take-in questions, you make your decisions or you pick your decision or your answer. So after picking your decision or your answer, then you have completed your selections. I said in an example that at the selection stage, you may be given yes or no to pick. There will be a question. For example, does the food taste good? If the answer is yes, then you pick it yes. That means you move to the next one to eat. Okay. But if the answer is no, then you move to the next one, whether to order for bangkun or rice or any other thing else to satisfy your hunger. Okay. All right. Now the last structure we saw was loop. Now loop also comes or taking questions. Now in loops, you continue asking the same question and you will continue to be getting series of answers that maybe is not the correct one. That means you have to start the process all over again. So the many times you are asking the same question, the many times you are getting probably uh, correct answers or wrong answers until you get the correct answer to it. Then you have completed the task. So let's take an example for a loop. Let's say you are solving an objective questions. Okay, so uh, the question is being placed there. Then there are options for you to pick. All right. So you don't know anything about that question. Okay, you not knowing anything about that question, the only thing is that you'll be doing what is called try and error. So you ask the same question, then you go and pick A. Then if the system mark it wrong for you, then you go back again. Then you pick B. If B is not the answer, then the system mark it wrong for you. Then you go back again. Then you pick C. Until you pick the right answer and the system mark it that yes, this is the correct answer. Then it means that you have completed that task. So in an objective test, you are doing and you are not getting the answer, and you are going in a cyclical manner, picking the answers one after the other. Sorry, picking the options one after the other until you get the correct one. Loop is just an example that I'm citing for that particular scenario. Okay, all right. Performance indicator, we are to describe the meaning of the term algorithm. So I'll try my possible best to describe it through definition and with some examples for your understanding, and also you going back again to teach your learners back in the classroom. So with an algorithm, we say an algorithm is defined as a step-by-step or well-ordered procedure for solving a problem. This is to say that algorithm is there to solve a problem. It is a type of program you have to write to just solve a given problem that you have counted or you are still encountering. Now, ask your learners in the class some of the problems that they are facing in the classroom or even at home. So, most of them may come up with some problems, even to the extent of what? Addition and subtraction of numbers. Now, if they are able to come up with some problems, then do ask them how were they able to overcome that problem. So as they narrate the step for you that, oh, I did this, I did this, I did that to getting this answer, or I did this and I did that to getting the problem solved, it means that that child is writing an algorithm. Okay, so the step-by-step procedure for that child to solve that particular problem is what is known as what? The algorithm. Okay, now algorithm is can be categorized. Okay, algorithm can be categorized on three principles. The first one is the input. The second one is what? The instructions. Then the third one is what? The output. In our elementary ICT classes, we actually know the term garbage in, garbage out. So algorithm also works with that principle. Okay. So when you see yourself in a particular problem and you want to solve that problem, then first of all you have to ask yourself, what input do I have to even start with? Okay, so when you ask yourself those questions, then you have to get an input to start with it. Okay, so dependent on the input that you have, okay, then you have to set instructions or you have to set the rules to obtain the desirable output that you want. Okay, so the output that you want will come from what? The rules that you set in the algorithm or in the process of writing the algorithm or the step by step of writing the algorithm. Okay, now let's quickly take an example so that you understand the algorithm for real. Now, our first example is this. The task is or the problem is my TV won't turn on. Okay, so I need to fix it. So that is the problem I am encountering. Okay, so my TV won't turn on. So what is the first thing that comes in my mind? Okay, so the first thing is what? I have to start from a certain place. Okay, now the first step here is called start. because in an algorithm, it is a program you are writing. So every program have a starting point. Okay, so is an appliances. Appliances have what? A plug-in point or a turning point or a switching point. Okay, so in writing an algorithm, you have to start from somewhere. So you start with the first step as what? Start. It means that you are now coming to begin to solve the problem. Okay. Then my second step is that I have to ask myself a question. If my TV won't turn on, then what do I have to do? I have to ask myself a question. Is it plugged in properly? So the TV, the cable, is it plugged in properly? So if the answer is yes, when I check, okay, when I check and I've seen that the plug is plugged in or the wires are plugged in properly, then I have to go to the next question. But if no, then it means that I have to what? Plug in the wires. Now, I'll go to step 3. Now, in step 3, I'll still ask myself again that is there batteries in the remote? Probably in step 2, yes, my wires are plugged in correctly, but still the TV won't turn on. Then it means that in step 3, I have to ask myself again that are batteries in the remote? Because I use the remote to turn the TV on. Okay. So if I pick my remote and I'm trying to press the button so that the on or the TV will turn on and it is not coming, I have to ask myself again that are there batteries inside this remote? If the answer is yes, then I have to move to the next step. But if the answer is no, when I checked and I saw that there is no battery inside the remote, then I have to fix in battery or I have to go and purchase a battery and fix it inside, then try it. If I ask this question myself that is there battery in my remote? If the answer is yes, then I'll move forward. If the answer is no, then I have to get battery into the remote. Now, the answer is yes. Let's take it that the answer is yes. Now I've checked and there is battery. Still, why won't my TV turn on? Then I have to go to step 4. Then I'll tell myself that maybe it is broken, so I have to return it to the store because that is where I purchased it. I have gone through all the steps for me to verify that my TV won't turn on. And I have come to the conclusion that yes, my TV won't turn on. Therefore, I have concluded that let me send the TV to where I bought it from to tell the person that oh, the TV won't turn on. So please kindly change a new one for me or fix it for me. Okay. So when you have returned the TV to the store, at the store, they can choose to give you a new one or they can choose to repair it, and that is all for you. Okay. So you end your what? Your algorithm here. Okay. So you end the algorithm by stopping. So this is how we write a simple algorithm to solve a problem. Okay. So you can still give this example to your kids. Okay, to bring out the possible questions that they may ask themselves to arrive at what the solution. And I know that at the end of everything, they might even say that let's send it to the repairer. Yes. So it's the same thing here. Okay, so you ask yourself the questions, then you are able to what, get the answers one after the other until you exhaust everything. Now, this algorithm is written by hand. Okay, so algorithm, you just have to take your pen, paper, and to write an algorithm. Algorithm is a step-by-step procedure in solving what a particular problem that you are facing. So this is my first example of an algorithm. So give more example to your kids so that they step by step they will bring out the solutions, okay, the possible play out outcomes, okay. But note that in an algorithm we have a start and we have a stop or exit, okay. So every program that you are writing, you have to have a start and you have to what, have a close or a stop of it, okay. Now let's look at our second example. The task is, or the problem is, I am hungry. So you coming back from school, okay, you are coming back from, or you've come back from school and you are pretty hungry and you went to the kitchen. Maybe you've seen a spaghetti there, yeah, and you said, oh yeah, I want to cook spaghetti, okay. So that is your first start because you already know what you are going to what, prepare. All right. So our first step is what, to start. As a programmer, you have to have a start, okay. Now the second step is that now I'm going to boil water in a pot. My third step is that when the water is boiling, I have to add my spaghetti or my pasta. And my step four, when it cooks for 10 minutes, because here is a process of what? Cooking. My step five, after the 10 minutes has elapsed, then I have to drain the water from the hot, from the pasta or the spaghetti. Then my step six, I'll add a sauce of my choosing. So you have cooked your spaghetti, then you put it in a plate. Then your sauce, any stew you have, then you do what? You pour it on it. Okay. Now, when you pour it on it finish, let's go to the step seven. You ask yourself this question: does it taste good? Yes, you have cooked the food. All right. When you tested it, does it taste good? If yes, then plate up. That means fetch it in a plate. You start eating. But if no, then there's an option for you to what? To pick again. Maybe you have to order for a pizza, or you have to order for a rice, or you have to order for banku, or whatever food that you want to use to quench your taste. Then the last one you stop because you have gotten all that you want here. Okay, so this is a step-by-step algorithm to solving my hunger problem. Okay, so I want to explain something very simple here. Earlier on, we looked at what? Sequence. We looked at what? Selections. And we looked at what? Loops. Okay, now when we look at this algorithm that we are writing, this is our second example. But let me use the second example to show you something. So we start from the first step, then we come to the second step, we come to the third step, fourth, fifth, sixth, seventh to the eighth. So all these steps here is described as what? Sequence. So each step you have to complete each step. So step one complete, step two complete, step three complete, up to the last step. So now let's come to where the selection is. Now when we come here, step 7, that is where what? Selection is. So in this, does it taste good? You ask a question. So if yes, then I have to plate up or I have to eat. But if no, then I'll order for pizza. Okay. We don't have the loop yet here, but when we go forward, I'll give you the example of the loop in algorithm writing. Now let's take the last example in third example. In a classroom, you might find a child who is unable to find the area of a rectangle. So as a teacher or as a programmer, you need to design an algorithm to solve that problem. So the first thing is what? To start the algorithm. Okay. So my second step is that I have to write an algorithm to read the length A. And also the third step, I have to write an algorithm to read the side length B. Now the side length A and B signifies the horizontal and the vertical lines of a rectangle. Okay. So there will be a number at the horizontal and there will also be a figure at what? At the vertical. So my algorithm should be able to read those two figures. Okay. Then my fourth step, I have to write the algorithm in such a way that I'll make area the subject so that area can calculate or can read the figures or the variables at A and B. It can multiply both of them to give me my area. So in my step 4, my algorithm that I'll be writing is that let area should be equal to side length A multiplying what? Side length B, which are the two variables that will be inserting in the program. Okay. Then after I have written this algorithm, then I will ask the algorithm to print the answer for the area, because in my algorithm I set area. I have set area to be my subject. So if my algorithm is able to read the two variables, the A and B, then my algorithm should be able to display the area for me. So in your step 5, you have to code it, or you have to write the algorithm that print or display area for me. Okay. So after that, step 6, then you code it as what? The program should stop there. Okay. Because you are only looking for the area for a rectangle. Okay. So this is a short algorithm that we write to find the area of a rectangle. And you can put this algorithm in C++ program and it will work very, very smoothly and efficiently. Okay. Now let's look at our second example and the third example. It may surprise you that some students, even back at GSS or even in GSS right now, can also sum up two numbers. So, as a programmer or as a teacher, you need to write an algorithm. Okay, you need to write an algorithm to solve that problem. So, in every algorithm, you have to start. Okay, now my second step is that I have to write an algorithm to read a variable of A and B, which signifies two numbers. Okay, which signifies what? Two numbers. So in my third step, I have to make a variable a subject. Let's say the C. I chose to bring the C there so that the C will be equated to my variables that I ask my algorithm to read as A and B. So it means that in the course of the program, when someone or a child or a learner puts 5 in place of A and puts 1 in place of what? B, I want this program or my algorithm to make C the subject, thereby adding A plus B. So it is going to give me what? 6. Okay. So in my next step, I want my algorithm to print the C for me to be my answer. Okay. So after printing the C, it means that that is what I want. So I have to let the program stop on its own or terminate it. Okay. So this is an algorithm to solve the sum of what? Two numbers. So colleagues, we have come to the end of describing what an algorithm abstraction, abstraction, abstraction in algorithm. So, what is abstraction? I'll go on by saying that abstraction is a technique of hiding unnecessary details from the user. The user is only given access to the details that are relevant. Example could be taken from vehicle operation or ATM operations are classic examples of abstraction in the real world. Abstraction is actually a technique for hiding some basic informations from an end user of a particular program or a software. You are not given access to all the informations that you need on a particular thing. Okay, now let's take example the vehicle operations and the ATM operations. Now, you bought a car, okay? You bought a car. The only thing that you need to know about the car is how to drive it, okay? So with that, it comes with a manual, how to drive a car. So they have already manufactured the car and you went in to buy it. So after buying it, yours is to learn how to drive it. Okay. So that is a classic example of what? Abstraction. You are allowed to only drive the car, but you cannot, okay, you cannot and will never fix it or know how and what goes into it before it becomes a full car. Okay, that is an abstraction. So abstraction is a technique for hiding some unnecessary details that the user don't need to know. Yes, to the user it is unnecessary. Okay, maybe to the programmer he needs those informations to complete his work or her work. A classic example again is the ATM operation or the ATM machine operation. Okay, you take your ATM card and you go to the bank to withdraw money. All you need to do is that you have been given the ATM card, right? All you need to do is just slot it inside the machine. Then you punch in the figures that you want to do. Now, after you punch in the figures, then you withdraw your money. So your money actually comes from the other outlet. Then you take up your money. Okay. But there is something hidden in that machine that you are not aware of. That is the programming aspect, and that is what we call what the abstractions. Okay, those things are hidden. They are deemed to be an unnecessary for you. Okay, so you have to just go and withdraw your money and go by. Okay, but the machine goes through a process to get you that money. All right, to get you that money. Okay, so this is everything about what we call what abstraction. So abstraction is just a technique for hiding unnecessary details from the user, and only the relevant ones are being made known to the user. For example, like phone, a mobile phone, or the computer that you are using right now, or the phone that you are using right now to watch this tutorial. Okay, now you purchase this phone or you purchase the computer or the laptop. You purchase the laptop. Yours is to just boot it on, use it for your work, watch movies, play music, you off it, then you put it down. But when you go into it, there are a lot of hidden things, parts that is in the laptop or in the phone that you don't even know. So those hidden things, okay, those hidden things are what we are calling abstractions. Abstraction is a simplified view of the world. Let's take the world for instance. Okay, we are taking the whole world for instance. Okay, the simplified view of the world. So when you take the picture of the world or the globe, you see that it is spherical, it is round. Okay, so that is abstraction for you. So is that you are taking the whole world as the whole world. But the pieces that comes together to make the whole world, it is not of use for you. Abstraction in a programming will make you know some of the things you should know and some of the things that you need not to know. That is abstraction. Now, in every abstraction, you need an input. Okay. Now, with these inputs, let's say you have a problem of collecting exam fees from your students. Anytime you ask teachers to collect the exam fee, They collect the exam fee and record it on piece of paper for you. And at the end of the day, some of the informations do not add up. Okay, or some at the end of the day, some of the monies also get what misplaced or missing. What are some of the inputs? The inputs are the names, the sex, the date of birth, the hometown, everything. Okay, those are the inputs. Okay, so after you are able to get all those inputs, after you are able to what collate all those inputs, then you have to what process it. Okay, so this is where the magic works. Okay, so you can take all these inputs, but in the side of processing, after processing, or at the time you are processing all those inputs, that is where the decision is being made that, oh, let me let color red be displayed to the user, let me let color blue be displayed to the user, but for color yellow and color green, they will never be displayed until such a time that I want them to what to know. Okay, so after that you give it to what to the output. Okay, so in an abstraction, you need inputs, okay, to process. So when you process it, then it gives you the output. So it's the same thing like you are manufacturing a phone, okay. So I need a screen, I need a board, I need the ICs, I need the battery, I need the slink body, the one that we use to design it, okay. Fine. So after you manufacturing it at this side, okay, at this side, now you tend to hide the board, okay. The board will not be seen, but it's only the outer view that you will see for the phone. The board will not be seen, but the outer side you will see for the phone, okay. And the screen, you will see the screen because there will be light and there will be parts that you have to touch. So those are the things that you want the customer to see. Okay, but the board and the ICs and the things that comes together, even the software even that comes together to run the phone, the user don't even know. Okay, so at the output side, the user just using just using the product without knowing what goes on in the product. Okay, but all that he or she needs is that the product is able to accomplish all that he or she needed that product to do for him or her. So let's take another classic example again. Let's take these two cars or vehicles here, like I explained earlier. So the first one here is using what is called abstraction. Okay, you bought a car, it is moving, it is doing everything. You are just to what? To drive it. And you are driving it, you love it. Okay? So everything here is good. Alright. Immediately you open the what? The car to check or to question yourself. What goes into doing these engines or the parts? Then it means that abstraction is no more working there. You need not to know this. Okay, you need not to know this. So programmers in general, they program in such a way that only things you need to know is made available to you. Thank you. Our performance indicator indicates that we describe the meaning of decomposition. What is decomposition? Now, decomposition comes first in the process of computational thinking. Per our previous algorithm that we've just looked at, decomposition plays a major part in the algorithm process. In fact, decomposition and algorithm move hand in hand. It means that when you have a problem, you have to decompose the problem into smaller pieces so that you can get your actual solution out of it. So what is decomposition itself? Decomposition means breaking down problems into sub-problems that can be managed and solved more easily. Computing, we are talking about what? Decomposing what? A problem. Okay, a bigger problem. Thereby, you have to break it down into smaller sub problems so that you can tackle them one after the other. Then, at the end of everything, you solve a bigger problem. That is what we are talking about under decomposition here. Okay, so sometimes decomposition is called the divide and conquer approach. It means that you have a bigger problem. Therefore, you need to what? Divide it in order to what? To conquer them. So as you are dividing it, it means that you are finding a solution to each of the sub problems that you are arriving at. Now, why decomposition matters in algorithm or in writing a program? So my first point here is that decomposition is very helpful in solving complex problems. Yes, so you might have a big problem, okay? Then you need to decompose those problems or that particular problem in such a way that you can solve it. Now let's look at my second point. In decomposition, we find the solution to sub problems, and by combining them, we solve the complex problem. Those sub problems that you have generated from the bigger problem, you end up by finding solutions to those sub problems. Thereby, at the end of the day, you are solving the bigger problem. That is decomposition for you. Okay. Now, the third reason why we value decomposition is that decomposition process goes hand in hand with what? Algorithmic thinking, in which you will provide a sequence of detailed instructions to solve a problem. Yes, decomposition moves with what? Algorithm. Algorithm is a step-by-step process or procedure that you employ to solve a problem. It's the same thing for decomposition. It is the breaking down of a bigger problem into smaller sub-problems to be able to solve the complex problem. So, algorithm and decomposition, they move hand in hand. Decomposition allows more efficient collaboration by allowing each team member to work on a sub-problem. Yes. In decomposition, some of the problems are bigger and very, very complex. So you need teams to also hold the sub problems for you so that at the end of the day, each team will come up with their solutions. Then bringing them together, you will be able to get or you will be able to find the solution to the bigger problem. So it enhances what? Collaboration between members or team members. Now, decomposing a big or a complex problem into smaller parts allow for more accurate debugging and testing of the solution. Yes. The smaller the problems become, the smaller you divide the problems, okay, the accurate it becomes, devoid of what? Errors. So that it will be very, very efficient to solving what? The bigger problem. Each team holding the small pieces will make sure that they are able to get the solution accurately, devoid of error. Okay, so that when you test their part of what? The problem, it will work or it will fit to what? To the bigger problem. Okay, now let's look at something very interesting. Decomposition always happen in our daily lives. But it's just like sometimes we don't actually know that it is even happening. For example, you plan to organize a birthday party with your friends. So, what is your thought process in providing the supplies and preparing for the event? So, the bigger problem here is what? The birthday party. Okay. So now, what are the sub problems? the sub problems that you are breaking them is the questions under that we start asking ourselves here. Okay, so the sub problem is, now I want to throw a birthday party. The first question I'll ask myself is, where will we gather? Which is the venue? Which venue are we going to rent for the birthday party? How many guests will be there? Or how many guests am I going to even invite? What will I serve for dinner? Because most of the time birthday parties goes into the evenings. Okay, so somebody will be there and have to take dinner home. Okay, or maybe eat it there before going back home. All right. Then the next question comes: do I have what I need to make dinner? So it's a question you need to ask yourself. Then the next question is, are my guests allergic to certain foods? Yes, you have to know. Some people might be allergic to alcohol. So you have to know the type of drinks you even bring under the birthday party. Okay. All right. How will I entertain them? So the entertainment, is it going to be the local drums or the jams or however you want to entertain? This question will come out with the perfect solution that you need. Okay. So when you look at my footnote under here, you will see that I said, after you answer all these questions, which is this one, all these questions here. So all these questions here also indicate what? The sub problems. Because the bigger problem is the birthday party. So the sub problems is when you are asking yourself these questions. So these questions becomes your sub problems. Okay. Then when you get answers to these sub problems of yours, it becomes the solution to the bigger problem or the main problem. I hope you get the understanding. Okay, so in everyday lives, we decompose problems to be able to solve it. In everyday life, we write algorithm to solve our problems. Okay, so it means that in our daily lives, we are faced with challenges that needs our computational thinking to work. All right. So ask your students to come out with some of the problems and ask them how they were able to solve it. Okay. Or they were able to decompose it before arriving at their answers. All right. Now let's look at the next interesting thing: decomposition and algorithmic thinking. We already saw that decomposition goes hand in hand with algorithm. Okay. It goes hand in hand with algorithm. Because when you are writing an algorithm, you are also decomposing. All right. So let's see the familiarity between algorithm and what? Decomposition. Now, in the previous example, yeah, okay, in the previous example that we just did right now, the birthday party, okay, after you break down the tasks that you need to do to prepare for the party, you will prioritize them. Yes. Okay. One have to come before the other. You have to prioritize them. Because if you don't put them into priority, you cannot know or you can never achieve the sequence that you want the thing to happen. Okay. So all those things you have to what? Prioritize them. Then the next thing is that in this process, you will define the priority of each task in a given time and decide which will be done first or which task can be done in parallel. Okay, so in algorithm and also in decomposition, you have to give what? A priority, which have to come first. Even the one that will come first is also have to come with what? Time. Okay, when this thing should be done, when that thing should be done. Or can this thing move hand in hand? Okay, so both decomposition and algorithm, they work in that particular principle. Okay, all right. Then the third similarity is that in your mind, you will design an algorithm to complete all the subtasks. Yes. So far as you are decomposing the problem, you are already writing what is known as what? Algorithm to the problem. So the questions you are answering or the questions you are asking yourself and getting the answers to them, you are already writing an algorithm or designing an algorithm in your head. Okay, so algorithm and decomposition, they move together hand in hand. Okay, so finally, you may have multiple algorithms, okay, for the whole problem, which is throwing the birthday party, okay, by designing one algorithm for each subtask. Okay, now you are decomposing, all right? So there are questions under your what? Decomposition, all right? So those questions are there to help you find solutions, okay? And those questions can also be your algorithm, okay? You can choose to develop an algorithm for each of the questions, okay? It's the same as what? Finding the solution to what? The problems, whilst you are decomposing the bigger problem into the smaller sub problems. Okay, so let's see how some of the subtasks can be decomposed, or you can write algorithm to that. Okay, so first one algorithm for place arrangement. Okay, the venue. Okay, where I want to hold the birthday party. So I can write an algorithm to cover that place. Where do I want to hold the gathering? Let's say five-star hotel, one of the five stars hotel. Then how will be the arrangement of the chairs? All those questions will come. Who sits at the high table? Where will the food be? Where will this and this be? So the placement or the place arrangement is also an algorithm on its own. Then you can also choose to write an algorithm for shopping. The clothes that you wear for that day, okay? The shoe and other things that you need to shop. You can write an algorithm for that. Then you can also write an algorithm for what? Cooking. The food. Okay? The food. Alright? You can write an algorithm. So you can do many more. Okay? Many more of the algorithm in this solving in this particular problem. Now let's look at one of the interesting examples again. Now I am faced to bake a cake. This is the problem I have. Okay, so in decomposing this problem, what should I do? I have to break this whole problem, baking a cake, this whole problem, I have to break it down into smaller sub problems so that I can find solutions to it. So my first question will be, what type of cake do I want to even bake? What type of cake do I want to bake? Do I have the recipe for baking the cake? Do I have the ingredients for baking the cake? What will I cook in it? So if I'm able to get the recipe and the ingredients, in what thing will I cook the cake in? Okay, so you asking these questions at your left hand side, you asking all these questions, it means that you break all these big problem into smaller problem, which is these questions. So when you are able to find answers to these questions, it means that you find the solution to solving the bigger problem. So let's see. Let's try to get the answers to these questions. So, what type of cake do I even want to bake? Okay, so I decided to bake what? I can decide to choose what? Chocolate cake, cheesecake, red velvet. Okay. Then my second question is, do I have the recipe? Yeah. So do I have the recipe? So yes or no or partly. Yes. So I can have the recipe for the cake that I chose. All right. Or sometimes I may not even have the recipe. Okay. Then I have to go and search for the recipe. Or maybe I may have it partly. I may know some parts of the recipe, but not all. Okay. Then that one too, I have to go and look for it. Okay. Then my next question is, do I have the ingredients? So yes or no, I have it. Then what are the ingredients that I'll need for baking my cake? Okay, all right. So I have sugar, egg, butter, and flour. The ingredients for my cake that I'm going to bake. Be it the chocolate cake or the cheesecake or whatever cake that you want to bake. If you answer these questions, it means that you are finding solutions to it. Now, what will I cook in it? So the cake, after mixing everything, putting everything together, what will I cook in it? So yes, I may choose to cook in what? In the oven or in the microwave or in the stove top. Okay, so that I can get my cake ready to what? To eat. So with you answering all these questions, it means that you have successfully answered the bigger what problem. All right. So I say after you answer all these questions or sub problems, you have a complete plan, which is the solutions. Okay, to bake a cake, which is the main what problem. Practice decomposition. Now ask your learners to think of a problem in any given domain, maybe math, science, everyday life. Okay, and explain how you answer or accomplish that by decomposing it into a subtask. In this session, we will take a look at a linear search algorithm. So, what does this algorithm do? This algorithm takes in two inputs from the user. It takes in an array and a data element. Now, before we dive in, let's look at some of the keywords. Our first word is going to be elements. Any unit of data defined for processing is a data element. Let me take it again. Any unit of data defined for processing is a data element. Example of our elements are account number, name, address, and city. So these are examples of elements in linear search. Now, let's take a keynote. A data element is defined by size, which is in characters, and type, which is alphanumeric, numeric only, true or false, dates, etc. So it means that our element comes in size, which is in character, and also comes in type, which is what? Alphanumeric, numeric only, true or false, date, age, etc. Let's look at our next word. Our next word is searching. Searching. So what is searching? Searching is the method of finding a certain item in a list of items. Searching for items or looking for or finding items in a list of what? Numerous items. Okay. All right. Then let's look at our last word. Array. What is array? It's a linear data structure that collects elements of the same data type and stores them in contiguous and adjacent memory location. So what we are seeing here at the down here is what we call array. Okay, that is what we call array. So array is like a container that collects the same type of data and store them. Okay, for it to be able to be what? Searched for. All right. Okay. Remember that I said in a linear search, you have two inputs in a linear search that you might employ. The first one is element and the second one is array. So without the element, array cannot exist, and without the array, element can also not exist. Okay. Now let's look at the part of array. The first part of array is the element. So elements are found in this array. Okay, so the elements are the numbers or the integers that are found in this array. Okay, now the whole thing here is called the array. Okay, this whole thing here is called the array, and elements are found in the array. Elements are found in the array. Now, the last thing about this array is the index. Okay, now what does the index do? The index gives the position of an element in an array. Index, they give position of elements in an array. That is their work. Okay, so our index normally starts from what, 0. Then it moves towards the right. Okay, so all these numbers here which denotes index shows position of a certain element in the array. Okay, so if you are doing a linear search, it means that we are going to use the index to search for the element in an array. Remember, an array is just a box or a container that collects the same data type. So this is an integer, which is the same data type. Okay, so if it is account number, that one too, it will only be for account number. If it is names, it will only be for names. If it is address, it will only be for address. If it is cities, it will only be cities. But in this array, or the example we are looking at here, is the same element of what? Integers. All right. Now, what is linear search? Linear search, which is also popularly known as a sequential search, is a process for finding an item in a list of items. Linear search is popularly known as what? Sequential search, because it moves from 1 to 2 to 3 to 4 and so on. So it doesn't jump, it doesn't make any random searching, no, but linear, step by step, okay, to finding of an information. Now, this sort of searching algorithm checks each element of the list one by one until a match is found or the entire list is searched. For example, let's look at our white background here. Now, when we look at this, the 39 here, it is our search element in our array. That means we are going to search for 39 in our array. Okay, so in linear search, the search begins from the first box, then it moves to the next, then it moves to the next, then it moves to the next until it locates the search element it is looking for. Okay, so that is linear search for us. All right, if the element is found in the list, the process is considered successful. So the search element is what? 39. So if it searches and arrive at 39, it means that the process is what? Successful. And the location of that element is returned. So this is the location of the element 39. Okay, so the index here is locating the 39. So yes, if you are looking for something or you are looking for the 39 on your phone, immediately you search for the 39, it will pop up that yes, we have found the 39. So location of that element is returned. Otherwise, the search is considered unsuccessful. So if the search begins from 13, the element 13, and it moves round through all these elements and was not able to locate 39. Let's say there is no 39 here, or we are searching for 10 and there is no 10 here, and the program is able to run through all the array and did not see any 10, then it means that it is unsuccessful. The search element you are looking for, or the search key that you are looking for, it is unavailable. Therefore, the system will have to also tell you that it is unavailable. Okay. Performing linear search. Algorithm of linear search approach. Now, in linear search, the index or search location in the specified array is found. So I always say that the index makes sure that you locate the elements that you are looking for in the search array. Okay. It starts the search by comparing the search key to the array or first list element. So here is it. So at the bottom here, your search key is element is what? 39. So it means that it will start from what? 13. And it will go, it will go, it will go, it will go until it locates the search key or the search element you are looking for. Alright. If the first element does not match the search key, the element, the next element, the next element, the next element will be compared and so on until the match is discovered or the array ends. If a search if if a match is discovered, the index is returned. Otherwise, it reaches the end of the array or list, indicating that the search key is not available or the search element is not available. Performing linear search again. Given array. So this is our given array. 50, 90, 30, 70, 60. Assume the search key is 30. So let's assume our search key is 30. Next, scan the array and compare each element to the search key. This. The array's first element is 50, but 50 is not equal to 30. Therefore, continue on the next element. The next element is 90, but it isn't equal to 30. So, it's time to move on to the next one. The array's next element is 30, which is the same as the search key 30, thus returning the index of the array's current element. So, print element is present in the array, indicating that the search key is available. So, all what this paragraph is letting us know is that when we assume that our search key or our search element is 30, it means that we have to do a check. So we will compare the 30 to all these numbers here until we arrive at the same 30. So when we arrive at the same 30, it means that our search is complete. We have found our element that we are looking for. Therefore, we want the system to give us or to print us the location of the 30. And I always say that the index gives us the location of an element in an array. Okay, now let's go to the second paragraph. The above example was the case where the search key was present in the array. Now consider a case where the search key is not present. Let's assume that the search key is equal to 10. Compare each element in the array with the search key. It fails to match the 50, the 90, the 30, the 70, and the 60, and eventually reaches the array's conclusion. as a result, return -1 or print element is not found in the array, indicating that the search key is not available. Now, the conclusion for this second paragraph is that assuming you are looking for 10 in this array and you compared all the elements in this array but doesn't match with the 10, it means that what we are searching for is unavailable. Therefore, it should return or it should give us the feedback that that particular search key or search element is unavailable. Now, remember that anytime you search for an element and you found it, it is return +1. That means you have found it. Return +1. But anytime that you search for an element in an array and you are unsuccessful or you did not locate that particular element in the array, then it is return -1, which also means that the element is not found or is unavailable in that particular array or search. Yeah, colleagues. So let's do some small function here. That means implementing C program for linear search. Now, when you look at the top here, I have my array, okay? And these are the elements in the array, and these are the indexes in the array. Now, we will represent index as a counter variable I in our function that we are going to write or have written, okay? Now, I earlier on said that when you are doing a linear search, you may have two inputs or you will have two inputs to use. The first one is what? An array, and the second one is what? The element. So you have to have an array and an element. So in my first function here, I am saying that integer. So we are looking at integers here, which is in our array. So all these things here are integers. Okay. So we are doing integer. All right. So we are saying that with the identification of integers in my array. Now, let's search through the array. Okay. We will search through this array. Then we will look for an element in the array. So I represent the element as x here. Okay. So it means that my first function is trying to say that I need two inputs to make my linear search, an array and also an element. So let's take, for instance, our element we are searching for is what? 30. And our counter variable will be on what? The I will be on what? 2. Okay. So if that is the case, let's open our flow down. Now, in my second function or coding here, I've written that for every search, which is the I here, the I here, for every search, the system or the program should start from 0. So I equal to 0. So it means that in my array, the search have to start from what? The first box. This is the meaning of this. Okay, so integer I equal to 0. It means that the search have to start from what? 0 here. Now, when we come to the next in the same function here, I said I less than array length. I less than array length. What does this mean? It means that I ranges from 0 to 4. So it goes all the way from 0 to 4. Therefore, I'm saying that if the search begins from 0, then it should move gradually from 0 to 4. Okay, so that's the meaning of this sentence here or the statement here. I less than what? Array length. So it means that I should what? Start from array length. From here, going to this way. All right. Then my last part here says that I plus plus. I'm saying that anytime I starts from here and anytime it goes to the next line, that means it is doing what is what? Increment of 1. It is adding 1. So when it starts from here and it goes here, it is an increment of 1. Then it goes here, an increment of 1. It goes here, an increment of 1 until the last one. Okay, so I am telling my program that when you are searching for the element in the array, please start from this place. But if you don't see the element in this, then please move to the next one. So anytime you want to move to the next one, please add 1 so that you can be able to move to the next one. So that it will help you check all the indices to see whether you can get the element in the array. So that is what this part is telling us. Okay, I plus plus. So anytime you make a move, you should add +1. Increment of what? 1. Okay. Then if so, then when you are able to locate the I in the array, then please, it should be equal to what? X. It means that when you are able to locate the I, which is, let's say, the 30, so the 30 is what? Our X. So it means that it should be equal to what? X. Therefore, if it is equal to X, and if you have found it, then return a message to me that yes, you have found it. So this is the reason why we have the return I here. It means that in this function here, the if statement, if I has been found in the array, then please equate it to X for me. So we are looking for 30. Let's say our search key is 30. So the program starts from here, it moves there, then it gets here. So realizing it that it has located the element 30, then it has to what? Equate it to X. So it will going to tell us that array I, which is 2, is equal to what? 30. Then if that is the case, then it will print it out that, oh, yes, I return I as what? 30. Okay. Then from the flow chart here up to here, it means that this program is complete here. And it means that this small function I've coded here, if only your element is found in the array, then this coding stops just here at my parentheses here, my braces here. Then it stops here. But in the case that you are not able to find your search key in this array, then you have to open another loop, which is this. So here you are trying to tell the system that if I start my search from 0, which is index 0, straight to 4, and I'm not able to locate my elements, then return a message that X is not found. So it means that return -1. Please take note that anytime you have +1, it means that your search is available, or what you are searching for is available. It is +1. But anytime you did not find what you are looking for, then it is what? -1. Okay, it is -1. So in this coding, we are telling the system that when you search through here and you are not able to find my element, then please return a message to me that, oh, what you are looking for is not available. X is not found, or X is not available. Then it means that it is -1. So return -1 is the coding, but this is a statement for you to understand that yes, this is what the system or this is the feedback the system is giving you. Okay, so this is just a small code that I have come up with for you to be able to do linear search. Okay, so take your students through this and let them be familiar with even early days. Take them through this, then they will be able to adjust to coding. The whole idea is that we want to sensitize their mind into this kind of coding, okay, so that they will be able to write an algorithm on their own and to be able to solve problems on their own to the extent that they can use the computer to solving a major or a complex problem in their life or in the lives of their loved ones.